Welcome once again to a tutorial on the BJTs, and here we're gonna basically discuss about the 8-parameter analysis of BJT based amplifiers. So we've just talked about what 8-parameter model is and how you can apply it and where you can apply it in our previous tutorial in the circuit theory section, or more precisely the two-port networks. But now in this particular video I'm going to introduce you all to the idea of treating BJT amplifier circuits as a two-port network. Okay, so whenever you're gonna perform the analysis using two-port networks, a BJT amplifier circuit that is, you're gonna find, or rather the engineers previously found, that the 8-parameter model was the best, okay, in analyzing the BJT amplifiers as a as a two-port network. Okay, so let's just start with the circuit of a BJT amplifier here. Alright, so here we are. Now if you look at the diagram on your left, then you'll see that we've just included here a very simple BJT based amplifier circuit. Now the thing is that, well, as you can see, we have a sinusoidal input signal source named as S, okay, and we've got two biasing voltage sources, DC voltage sources, that are used for biasing the BJT, okay, that is VBB, that's at the input end, okay, and that just biases the base and the emitter junction over here. And we've got another voltage source, DC voltage source, that is VCC, biasing the collector and the emitter area. Okay, so now the thing is that, or rather keeping the collector base junction reverse biased. Okay, now the thing is that, we are gonna deal with the common emitter mode amplifiers created using BJTs, okay, because they are the most common types used in a multitude of applications as such. So we're basically going to be explaining the entire treatment of a BJT amplifier while in the common emitter mode of operation. Okay, so now let's just look at this circuit over here. So we can see that due to this kind of a setup, whenever this circuit is just turned on, or the power to the circuit is just turned on, then you're going to be obtaining an input voltage across the base and emitter terminals over here. Let's just call that V in. Okay, and here you're going to obtain across the collector and the emitter an output voltage known as VO or Vout, whichever way you might want to express it. Okay, and there's also an input current that is going to enter into the BJT through its base. That's just known as, let's just call it I in. Okay, that's better. And there is also an output current, okay, or rather the collector current that just flows in the outer loop or the output loop of the circuit, directed somewhat this way. Just call that IC, okay, since it's the collector current, or rather we might call the input current as IB over here, and that would just sound better because it's actually the base current that is going in. Okay, so this is the entire setup of this particular circuit, as you can see. So what happens here is that in order to amplify this particular signal coming from this signal source S, which is of course an AC signal, so this is an AC signal, okay, an AC source. So in order to amplify this particular AC signal, we need to set up the BJT circuit with all the biasing voltage sources, which are actually DC voltage sources, so that the amplification can take place. And as such, if we would send a small signal, okay, somewhat like this, we're going to get practically a larger signal at its output across its collector and emitter terminals. So this is basically the idea of the entire circuit, and that's how the BJT would work as an amplifier. Fine. Now, as I said, we're going to explain how to treat this BJT as a two-port network. Okay, so now let me just tell you that there are certain non-linearities involved in the BJTs. Okay, whenever you're just working with the BJT and using them as amplifiers, there are certain non-linearities that you might encounter due to temperature fluctuations, their reverse saturation currents, and also certain factors like the variation of the transistor beta, or the amplification factor from one type of device to the other. So all these factors come in and create this bunch of non-linearities that is going to affect your signal whenever you just obtain it out of the output terminals. And in many cases you see that your signal is going to suffer from distortion. This is going to create some distortion in your signal, so that the output signal is not exactly a copy, an amplified copy of the input. So the thing is that whatever is followed conventionally is that the input signals are always kept at small magnitudes. Okay, so the BJT can take only small valued, or more precisely small magnitude AC signals as input. Okay, otherwise the nonlinearity is going to creep in more. Okay, and that's why, due to this particular reason, the BJT, the H parameter model, which actually tries to analyze the BJT amplifiers, okay, whenever they're trying to amplify certain input AC signals. So that's why they're this kind of an analysis is also well referred to as the small signal analysis of the BJTs. Okay, because the BJT always can handle small magnitude signals at its input whenever it's just amplifying. Okay, so it's also called small signal analysis. Okay, so in this particular method of analysis, we're not going to include any of the the DC biasing voltage sources that are present over here. So we just got rid of the DC sources. Okay, oops, I just forgot to rub these out. Okay, so now what happens is that the entire input current, or the input voltage, and even the output voltage and output currents, they're all dependent upon this input supply source, okay, that is just supplying the input AC signal, and the BJT's performance. So under such a situation, we're gonna basically check, or rather find or learn how we can analyze the BJT's performance as according to the H parameter model. Okay, so now we know that in case of H parameter model analysis, okay, we just look at an H parameter circuit, or a two-port network more precisely, as somewhat like this. We just take it as a box, assume that there's some circuitry inside, and we have two input terminals and two output terminals. So these are the input terminals, okay, and these are the output terminals. There you go, and this is your circuit. Okay, or more precisely, I'm just going to write that down over here. So this is your circuit. Okay, and you have an input current and an output current, okay, known as, let's say, just call this input current as I1 and the output current as I2. And similarly, you get two voltages also, that is the input voltage known as V1 and the output voltage known as V2. Good. Now what happens is that depending upon this particular method of analysis, we just land up with two equations. Now these two equations, that is 1 and 2, as you can see on your right, tend to describe the entire behavior of this particular two-port network whenever we are actually trying to analyze this circuit using the H parameter model. Okay, now you can see over here that only the variables, that is the input current I1 and the output voltage V2, they are just treated as the independent variables. Okay, so I'm just going to write that down over here. So they're just treated as the independent variables. Okay, and we also have certain dependent variables as well. So other than these, that is the input voltage and the output, input current and the output voltage, we have the input voltage V1 and the output current I2. So these two variables are just treated as the dependent variables. So they depend upon the value of the input current and the output voltage, right? And all these H11, H12, H21, and the H22 variables that you can see over here are the corresponding H parameters that we have been talking about. So over here you can see all the H parameters and what their physical meaning is have been just given over here onto your left. Okay, now we're gonna basically treat the transistor or the BJT as a two-port network. So let's just check it out how that happens. Okay, so if we just take the simple BJT, now looking at this particular circuit from wherever we just started, we're just going to take this particular NPN type BJT. Okay, so let's just take it over here. So we're gonna take the BJT. There you go. And this is its input base terminal. Okay. Now if we just draw two lines over here. Okay, we're just gonna draw two lines. Okay, take the emitter and make it common. Since we're working with the common emitter mode, so it should be commonly available to the input and the output terminals as well. So there you go. Now looking at this particular circuit that we've just given out over here, we can just see how we can basically treat the BJT as a two-port network. So this is the same transistor T1 that we've just illustrated in the previous circuit. So this forms the input terminal right now. Okay, and now these form the input terminal, that is, and here we have the corresponding output terminals of the BJT circuit. So this is how we can treat the BJT as a two-port network. Okay, so there you go. Now similarly, like a two-port network that I've just given over here, it is also going to have some input currents and input voltages and correspondingly output currents and output voltages. So for the BJT, we're going to write them down as so there we go. So for the BJT, we can see that the input current is just treated as the input base current. So here IB is the same as that of the I1, okay, in the H parameter model, and VB is the same as V1, okay, and here IC is the same as I2, whereas VC is the same as, well, the V2, that's the output voltage. So we can just see how we can treat the BJT as a two-port network. Now extending this idea to the H parameter analysis, okay, so whenever we just try to analyze this particular BJT amplifier using H parameter analysis, now this method has certain advantages. Okay, now we can actually find out its input impedance and then output admittance and the current gain and their interrelationships with each other using this particular method of analysis quite well. Okay, so that's why this method has been adopted over here. So whenever we're just gonna treat, okay, I'm just gonna box this up so that you people just get the idea of whatever I'm just trying to do. So this is your black box or the circuit, okay, that is being just treated as a two-port network. Okay, so now whenever we just begin to analyze this particular BJT circuit, then we're going to land up with a corresponding H parameter equivalent circuit of this particular device. Okay, now the two-port network analysis leads us towards that direction, and it just gives us, so as you can see over here to the figure on the right, we can see that the H parameter analysis of a particular circuit, okay, gives us an equivalent H parameter circuit, or rather an H parameter model for a particular circuit, or rather any circuit that you can analyze with this particular model. So we're going to obtain a similar one for the BJT also, but before we do that, we need to find the corresponding H parameters. Okay, so now let's just write down the two equations. Okay, so here we are. Now these two equations are not generalized anymore whenever we're just talking or maybe treating the BJT in terms of the H parameter model. So these suffixes should actually, or rather the subscripts over here should actually change. So we're going to change them, okay, according to our BJT model. Okay, just hang in there for a while while I just make it the way that it just works for the BJT H parameter model. Okay. So now as we can see here, the input current is basically IB. So here the input current is IB, okay, and the output voltage, as you can see here, is VC. And note the the subscripts that I'm just giving over here. So all of them are in the lowercase notation. So this lowercase indicates that we're working with the AC signals, okay? And if we worked with DC signals instead, then these letters would have been in the uppercase formats, okay? So now that we've just done this one, now the dependent factors or dependent variables are of course the input voltage, that is VB over here, okay, and the output current, that is IC. All right, there you go. And now the H parameters that we have over here, now different H parameters, we've got, well, 4 of them. So 4 of them have different notations. So the first H parameter is just written down as, well, HIE for a BJT. The second one goes somewhat this way. It is just written down as HRE. The third one is HFE. There you go. And the fourth one as HOE. Right? Now you must be wondering as to what each of these H parameters actually stand for. Well, they mean the same thing, okay? But I'm just also going to include their mathematical significance over here. You see, the term or the H parameter HIE is actually, so here HIE is mathematically expressed as a partial derivative of the input voltage with respect to the input current, okay, under the constant output voltage, okay. It's just obtained from the two-port network analysis by just, shorting the output terminals as such. And this particular term is just defined as the input impedance of the BJT, okay. Then we got the term HRE. Now, HRE is basically expressed mathematically as the partial derivative of the input voltage with respect to the output voltage, okay, under constant input current, that is with the input terminals basically shorted out, okay, under the H parameter analysis. And this is termed, this particular H parameter is termed as a reverse voltage amplification factor. You see, these H parameters that we're just obtaining over here, they just actually explain certain properties of the BJT devices, okay, that are used very frequently while analyzing BJT based amplifiers and their performances, okay. So other than these, we got 2 more H parameters over here. Now we've got here the HFE, that is, well, expressed as a partial derivative of the output current versus the input current, okay, under constant output voltage, and is termed as the current gain, while we got the last H parameter, that is the HOV, expressed mathematically as the partial derivative of the output current with respect to the output voltage, okay, under constant input current. So this is known as the output admittance. So with the combination of all these 4 H parameters, the BJT is expressed as a two-port network using these 2 particular equations. So in that case, I might like to call these equations as equations 3 and 4 because it's especially the case for the BJT amplifiers, so they're especially applicable for that particular purpose. Okay, so now that we know what the various kinds of H parameters are and their physical significance as well as mathematical significance, and the equations that apply for the BJT while it's being treated as a two-port network under the H parameter analysis, we're going to take a look at the equivalent H parameter model that we could obtain for the BJT in this case. So with this particular equivalent H parameter model for the BJT, we can use this particular model to analyze any kind of BJT amplifier in various configurations as you might find in a particular circuit. Okay, so now using this model, a lot of complex analysis is easily possible, and you can, whenever if you just take a look at this particular circuit that we've just shown at the beginning, we just excluded the biasing resistors and all. So if there are complex circuits for the BJT amplifiers like that, you can easily extend this particular model of the BJT in terms of H parameters and analyze those complicated circuits with ease. Okay, so lastly, I'm just going to tell you one more thing over here, that sometimes you'll find common base and common collector type configurations of the BJTs also existing in few circuits, and they also are applied in some sort of amplifier based applications as such. So if you ever encounter any kind of that type of circuit, okay, then you can extend the BJT H parameter equivalent model, although it's in the CE mode, okay, you can even extend this particular model to analyze those circuits. Now in that case, all these H parameters in terms of the formulated with the collector, I mean the common emitter mode in mind, can be used in order to derive the H parameters of those other configurations. So I've just included here a table, as you can see. Okay, now this table actually summarizes the interrelationships between the H parameters obtained for the common emitter mode and with those that we must obtain for the common base and the common collector modes whenever we're working with those kinds of circuits. Okay. Now that said, we just would like to wind up our discussion right over here, and we're going to bid you a short goodbye. Now you're going to keep watching and learning even better. So don't forget to check out our next tutorials, and I'm going to see you right over there. So for the time being, just bye-bye.